So really happy to introduce to you Josh Dolence, who is from Los Alamos National Laboratory, but also one of the founding members of the Los Alamos Michigan Spark, which is Los Alamos' permanent presence here in Ann Arbor. And just like Los Alamos has Z numbers, we call him M00001. So he was the very first person to move. And now we have about 4 scientists here in Ann Arbor, and he's one of them. So by way of background, so he belongs to the computational physics and methods group at Los Alamos. And he received his PhD from University of Illinois at Urbana-Champaign in 2011. And he spent 3 years at Princeton University. And his research areas in terms of domain is computational astrophysics. Mainly, he used to look at black hole accretion and supernovae. And since after he came to Los Alamos, his research interests and experience and expertise grew quite broadly. And so today he's going to be talking about Parthenon, which is, along with his group, he's been putting together this flexible framework that you can use to develop rapidly develop performance portable multiphysics codes for a wide range of applications. And one of the things, I don't want to speak for you, but one of the things we look forward to...
By all means, I can just sit down.
I think one of the things we're looking forward to is for many potential collaborations to spring from the discussions that hopefully originate today. So with that, thank you, Josh.
Yep, thank you, Karthik. Is the sound okay?
Yeah.
It's good for everybody? So I just got to say, I sure wish that all those zeros you mentioned were like reversed and I had one, anyway. There's a lot of zeros. Yeah, so thanks for having me give a talk. I've been here since June, so it's sort of about time I meet a lot more people and start talking about potential collaborations, which I'm very excited to discuss with folks. I see some familiar faces out there, which is good, and lots of new faces, which is also great. So yeah, as Karthik said, I'll be talking mostly about Parthenon, this AMR. I shouldn't really call it an AMR infrastructure. It's really an infrastructure for writing multiphysics codes. It does AMR, but it does lots of other things, as we'll discuss. And I think there's a lot of opportunity for folks to get back to writing codes sort of from scratch, as I think I'll describe, in a way that's super productive. And hopefully I'll convince you that there's opportunities here that won't sink like an entire grad student's career into writing a code that can go off and solve a pretty complicated problem with sophisticated methods and so on. Before I get to that, though, as Karthik said, I just wanted to have a slide. I figured it was worth just spending just a minute. So Los Alamos National Lab is now also at the University of Michigan. I think some folks in the room certainly know they're involved. And I know from the Lano side, I won't speak for Michigan. Lano side, we're super excited about what that means for opportunities for collaboration. And so part of my job here as the first one and now one of 3 who's actually on site officially is to build bridges, right? To find opportunities for us to collaborate. So we're doing lots of things to support that, including a bunch of events that I list here, colloquia and various kinds of tea times and things like this. I wanted to list this stuff more or less to say, if you're interested in staying engaged and hearing what's going on, hearing about the things that we're organizing, please reach out to me. We can add you to a list and make sure that people stay informed about what's going on, because I don't know how else to engage such a big community as UM. I also wanted to just point at faces. Daniel Israel, who I saw come in, he's in the back there, was the second, so he's 000000002. And Patrick Mullen. Patrick just arrived here like about 3 weeks ago. Didn't see him come in, but so we've got 3 now. There are others coming, so by roughly June we'll have 6 staff and 2 postdocs. Those are the ones we know about. There are other people being talked about, but the plan in the end is for, I say 100 plus, like, by 2030, I don't know what meaning numbers really have anymore, but the publicized number is like 200 by 2030. So that's 2 things. It's a pretty quick ramp up, so we hope to grow pretty quickly. that's going to depend on us building these bridges, right? People are going to come if they see exciting collaboration, so I wanted to highlight that. But by the time we're done, if we get to the size, we're going to be a pretty significant presence in terms of research at And so we're coming. Hopefully that's a good thing for everyone. Okay, enough of that. So agenda, I wanted to talk about, like I said, Parthenon. Karthik warns me that if I just talk about code, though, that by like halfway through the talk, everyone's going to walk out. And so I'll try to touch on some of the applications a little bit as I can. And that won't be super deep, but I'm happy to talk about all this stuff sort of offline. There's lots of things that, that we do with Parthenon base codes. So first, some background and context. Why are we doing this? I'll give a little introduction. What is Parthenon? Just like, what does it actually do for you, and why should we care? I'll take a few little deep dives. The deep dives are meant to highlight what I think are kind of unique features of the code base that are enabling, at least for certain applications. And it'll also serve as a sort of an example of the way Parthenon gets developed, which is, as I'll get to, sort of very application driven. We don't have some like abstract notion of a perfect infrastructure. We're writing codes to do physics, and as we need things, we develop it, and that's sort of the way Parthenon has come about. And then I'm gonna like kind of sprint my way through order 10 codes that are already out there, many of which are open source that are built on Parthenon that do lots of different things. And I'll spend a little bit more time on a couple of codes that we've been developing at LANL and now at Michigan that are, I think, potentially good places for us to collaborate. So.
It might be nice to maybe pause after each of the sections so there's some interaction.
Sure.
Instead of waiting all the way to the end, if that's okay.
Yeah, no, I'd be happy to have people jump in, throw things at me, whatever you want to do. Okay. So, yeah, I started this talk, I had like, I don't know, 3 slides and then 5 slides and then 10 slides on like LANL challenges. There's a whole another talk I could give on challenges at LANL. We got a lot of them. We do a lot of complex things and it's tough to do. I ended up trimming this down to basically 1 slide. And what I really want to communicate here is that in the space of sort of computational physics, computational engineering, computational problem solving at the lab, it's like totally central to what we do. It's an absolutely core capability to what the lab does at this day and age. To carry this mission out, we lean heavily on codes that have been around for a long time. You can imagine like the things we do are complicated. There's sort of a lot riding on the results of these codes. And so there's sort of a lot of V&V and these sorts of activities that build trust in these capabilities. What that's produced are codes that are order 1 million lines long, and they've been in development for decades. So like at some level, that's like an enormous success. We've got these codes that have been around for decades solving complicated problems. That's great. But that leads to problems. And the problems that I'm going to highlight here, there are other problems, but highlight some of the problems that I see that I think Parthenon helps address are around sort of agility. How do you bring a new staff member, for example, at the lab, or a student who comes for an internship? How do you bring them up to speed on a code that's 1 million lines long? It turns out like very few people really know what's going on all throughout the code, and that's a problem. You should know what your code is doing. It's sort of a core piece of computational physics. New capabilities, it turns out, are really difficult to add. Like you try to add a new method or a new physics module or something, and it turns out that it has tendrils, right? It touches so many things, and it gets really difficult to put something in new and know that you've touched all the places you need to touch and get it to work the right way. There are pervasive physics and modeling assumptions. So X-range is a code, big code a lot of people have heard about. One assumption it makes is pressure temperature equilibrium. Pressure temperature equilibrium, it turns out, is an assumption that got baked in so deeply that it's actually very difficult to go through and undo that assumption. You have to like just search far and wide, and you're never quite certain that you got every place where you made that assumption, right? So like it can be problematic to have this much code to go through. Data structure and algorithm choices in a code like this that have been pushed on for decades. If you want to make a change to these things, you've got 1 million lines of code, and you've got to touch about 1 million lines. Like these are not things that are abstracted. They're everywhere. You know, you got to touch every loop and every data access, all these things. So those are a problem if you need agility, and I'd argue that in fact agility is essential. The mission's rapidly evolving. There are questions we have to ask, like, okay, we've had these codes for decades, they've been solving important problems, but are they still the capabilities that we need? Are there new problems we have to solve? And there are really good reasons that are mission-driven that suggest that, in fact, we need to move beyond some of the capabilities that we have. We need to do better physics models, much higher resolutions, all these things. It's hard to do that without agility. Workflows are rapidly evolving. I had to drop AI somewhere in my talk. This is the only place I've dropped AI. So workflows are changing. Are the codes that we have the right codes to support those kinds of workflows? And of course, computers are rapidly evolving. If you have 1 million lines of code, and when you started writing those 1 million lines, GPUs were like not a thing. What do you do? It's a really hard challenge, actually, to imagine how you, in place, port a code to use a new architecture. And the pace at which they're changing means that you'll just never keep pace. You can never keep up. And so, also a problem. The challenges that I think are related to the nature of big codes and complicated machines and all this stuff go beyond Lanel, though. So I just wanted to highlight a few that maybe hit closer to home for some folks here. I would argue that 10 years ago, you could sensibly put a grad student on a project of writing a new code from scratch. It was a big lift even 10 years ago. There's lots of pieces. You got to worry about I/O and all these things that are not super important to the physics problem or whatever that you're solving. But you could do it, and it was a valuable experience. Now, it's not so clear to me that that's really tenable. There's too many things you have to know too much about. It ends up taking too much time, and the student doesn't get to do the science or whatever it is that they're trying to do. So that's a real issue in my mind, because I think you have to start asking questions like, is it reasonable for a research group to have its own code, its own in-house code that it knows up and down, that it maintains, that it adds physics capability and so on too. How do you train if you don't have a code in-house, if you don't have students writing codes? How do you train sort of the next generation of computational scientists? It's not clear to me. I think it would be kind of disastrous for the field if we end up in a space where all we have are sort of sophisticated users of codes. But what do we do when that code is no longer the code that we need and we don't have the people trained? So these are issues that I see, at least, that I think are important to solve. And I think Parthenon and codes like this, this is our version of a code that I think can help address this. I think there's an impact that we can have here. All right, so on to Parthenon. So I wanted to start sort of with the origin story. We don't, nobody does anything really from scratch anymore. All ideas have been explored. Everything has been done. So where did Parthenon come from? It sort of started with Athena++. If you're in the Astro community, you've almost certainly heard of Athena++. It's sort of a very popular open source code that came out of Jim Stone's group, who was at Princeton's, now at the Institute for Advanced Study. Jim has a history of releasing codes that have really widespread usage, and there's lots of good reasons for this. Athena++ was a really nice code for lots of things. It turned out to be super fast on CPUs, and then GPUs became a thing. And Athena++ did not run on GPUs. They didn't really have a path that was obvious to port that code. They had lots of people adding physics packages and so on. It got out of hand, and it was hard to imagine how you port it. Along came Philip Greta, one of our collaborators. He was actually at Michigan State, so yay for the state of Michigan, I suppose. He took Athena++, and he took a very narrow slice through the code and added Cocos. So show of hands, this will be helpful for me. How many people have heard of Cocos? Okay, actually most. Great. So Cocos, for those who haven't heard of it, is it's a performance portability layer. It's a library that offers abstractions where it defines data types, it defines mechanisms for writing loops that are so-called performance portable, which is to say that behind the scenes, your code will be compiled into code that can execute on a CPU when that's appropriate, or a GPU when that's appropriate. And the folks who maintain and develop Cocos are sort of responsible for all the stuff, all the magic that happens behind the scenes that translates what you wrote into code that can execute on these different architectures in a optimal, in quotes, way. So Philip took Athena++, took a narrow slice through it, got K-Athena or Cathena out of this, depending on who you ask. What he showed was that you could take that narrow slice and get a code actually that performed really well. The basics of Athena++ actually were really well aligned with using GPUs. It was just that the code wasn't written that way. It didn't use these data structures, these abstractions. There was a lot of code that you had to deal with. But if you could do it, then you'd have a code that in your hands that actually worked really well. So we saw this, I have a history, with Jim. I was at Princeton for a while Jim was faculty there, so like I knew Athena++. All this stuff came together with this last one, which is one of the things that I was heavily involved with back when we started this was the X-Rage code that I already mentioned. It's a cell-based AMR code that does lots of physics, all the physics under the sun. Basically, here's an asteroid impact simulation with that in the ocean. There's been a long-standing discussion about X-Rage as a code, and in particular around the sort of very fundamental decision that they went with, which is to use a cell-based AMR mesh. So a cell-based AMR mesh, in some sense, is sort of optimal. The idea is you have a mesh, locally, each cell, you can decide, okay, I should refine. And so you just refine right there in that very, very, very narrowly isolated location. And you can imagine if you do that over and over in lots of different spots in the mesh, what you end up with, while it is in fact a structured mesh, there's a structure you can define to it, sure feels a lot like an unstructured mesh. And the mechanisms that you use to loop over it turned out to be super inefficient and problematic. So there was interest in asking the question, can we do better? Are there other approaches to writing an Eulerian AMR code that might get over those hurdles, but still be viable for running the kinds of problems that LANL cares about? And so, this question had been asked for a long time. There was finally, at this moment, just fortuitously, some will to actually answer it at the same time that we saw this stuff coming through. And so, opportunity. We started up a collaboration that became Parthenon. Parthenon is sort of our answer to this question. So what do we produce? So I promise I won't have all just walls of text. So Parthenon, as advertised in the title, right? The idea here is that we wanted to write something that made it so that, for one, we could answer the question that we were being asked. Can you write a code that doesn't use cell AMR, that uses something that's better for machines, that runs faster, but you can still do all the physics that you care about? So that was the sort of immediate need. But we had bigger ambitions, right? If we're going to go off and write something, like let's write something that's useful to a broader set of folks, because to us it seemed like it wouldn't be dramatically more difficult to do that than to write our little one-off code. So we aimed to write something that could serve our needs, which are very diverse. We have a lot of different physics packages that we care about, a lot of different kinds of discretizations. We've got things on finite volume stuff and cells and faces and so on. We've got particle stuff. We've got lots of stuff. So you got to worry about all these things and how they interact, and you want it all to be performant. And so what we did was we tried to put this together sort of in a generic way, that we could write our code that would be extensible and sort of future-proof. That's a dangerous word, of course, but future-proof as much as you can. And that other folks could do similar things with their own physics and their own interests. And the way we sort of ensured that would be the case is we had collaborators on the outside working on totally different codes with their own totally different interests. And we were sort of co-developing Parthenon so that it served all of our needs. And so that process was sort of useful. I say here it's a community effort. What does it provide? So mesh manager with AMR, it does load balancing, all the MPI, communication with the ghost cell, kind of that stuff. It moves particles around. Handles I/O, both input and output, so like HDF5 and Ascent and various things like this. It's got data structures to store and organize mesh-based data and particle data. Lots of facilities to sort of dice and slice your data in lots of ways to make it, to get access to the stuff you need in a way that you can interact with it performantly. We've got linear solvers actually written directly in Parthenon. No one's actually bothered to hook up something like Hyper or something, but you totally could. Memory management. We have a form of task-based parallelism we'll talk about. Abstractions to represent loops. These are basically wrappers around Cocos that are built specifically for Parthenon and allow you to actually, under the hood, sure, you can use Cocos, but maybe you want to use OpenMP, or maybe you just want to do, whatever, SIMD loops or something. You can write all those things under the hood. And finally, adjustable parameters. And those adjustable parameters turn out to be super important. I'll talk about this in a minute, but performance portability is actually not true. Like it's a lie. It doesn't exist. You can't do it. What you can do instead is you get portability and bake in parameters that give you performance portability. And so this is our version of that. I wanted to mention, so we've got roughly 30 people who've contributed. We had a developer meeting a few years back. I'd like to have another one, and I'd like to do it here. So if there ends up being anyone interested, that might be a time when people could come out and learn some things, start to play around with it. We actually had somebody come to our first one who had never touched Parthenon, and by the end of the week-long workshop had written a transport code. And that person, turns out, is Patrick, who, again, still isn't here, but he's actually now at Michigan. So yeah, that can be useful for folks who are interested. So I'm going to quickly go through some design considerations, things that we were thinking about when we wrote this code. So we wanted it to be fast, this is sort of obvious, and we wanted to enable a wide variety of numerical methods. Again, this is like we can write something that we think can serve lots of different needs. What that led us to, and obviously part of this was that Athena++ was a thing that we knew about and we knew that it worked. What this led us to, though, was a block-structured code, structured grids. Very simple IJK indexing. It's super friendly to memory subsystems, which is like the bottleneck in almost every multiphysics code. It's just memory access. And so we can support super high cache throughput, vectorizations basically perfect. All these things that you care about are very well supported by a structured mesh. So that's how we ended up with that direction, is thinking about we wanted a code that was fast and supported basically everything we could think of in terms of numerical methods. Yeah, there's this comment I made already, performance is not portable, at least not trivially. And then with that in mind, you can't really write a code of any sort that solves everybody's problem. And if you try, you actually won't ever produce a code. I've seen this happen. Like you can try to solve everyone's problem, and instead you solve no one's problem because you're just focused on being so general. So that wasn't really our goal. Our goal was to solve many people's problems. And then where we thought, you know what, maybe somebody's going to want something different than we have, provide a point of customization. You can inject something. And I'll show some examples of this in a bit. Yeah, so AMR has been around for a long time. It's sort of an obvious requirement for the kinds of things we do, but that's not enough adaptivity. There's more adaptivity in what I'll call sort of classical adaptivity. There are all kinds of methods out there now that are less classical, less familiar. This is just about being smart about how you manage memory, where you put things, and I'll talk about some good examples of this in a little bit. We obviously wanted it to be scalable. For us, that means there are lots of capabilities out there that try to hide communication from you. All the network stuff, they try to hide it. Bad idea. It's exposed, it's easy, but you know exactly when you're calling it, and that was crucial for us. Physics agnostic, nothing in Parthenon is physics. There's no physics at all. It's basically just sort of math and algorithms. Yeah, modularity, we've got ways to do that. We can talk about later. And again, it's application driven. So we designed to a need, not to some abstract picture of what our code should be. So just to briefly, block AMR, what is it? In case you haven't seen something like this before. So the way to think about block AMR is that the mesh is just composed of sort of logically rectangular blocks of some fixed size. So for us, we often will work with blocks that are, say, 32 cubes. So there's 32 cells in each dimension, and you can compose a mesh out of those blocks that physically can be different sizes. And so you can get pictures like this. On the top, you've got a mesh that is composed, I think these are 16, this is 2D, so 16 squared blocks, 3 by 7. So you got 21 blocks, and it represents a mesh of some particular size that would, it's equivalent of a uniform unigrid mesh of that many cells. In the context of block AMR, when you refine, what you do is refine a block. That operation takes one block and turns it into 4 subblocks, or basically factor of 2 refinement. So dx is halved, and you produce 2 to the d blocks. So this is refinement over some part of the domain. You get a bunch more blocks, and then this is one more refinement on some subset thereof. So this is kind of the basic picture in block AMR. There's little details, like you want things like proper nesting, which is just to say that no 2 neighboring blocks differ by more than a factor of 2 in resolution. That's actually not strictly necessary, but it is a nice feature, and it avoids some issues that you can run into otherwise. One thing I wanted to mention, this is sort of a convenience thing, but like blocks provide like the sort of perfect chunk of work, it turns out, and there's a built-in parameter. What is the block size? So it provides a mechanism you can ship data around in chunks, right? So you can use this for load balancing. If people have ever thought of like loop blocking and all kinds of these transformations that you make to make your code faster, this is sort of baked in to block AMR. There's sort of a natural mechanism now to control the granularity of the data, and that has lots of uses. All right, so that's kind of the basic story. That was my basic story of Parthenon. Provides lots of things that nobody in this room probably wants to write, which is useful for you if you are trying to write a code. And we did it in a way that I think lots of people can use. Now I'm going to start talking about specific features that I think are kind of I think quite powerful features if they happen to apply to your problem. And of course, we've been developing these things for our own problems, and so there definitely are use cases for this stuff. Some of which are, I think, a little bit clever, and so you might discover that if you think about this for a minute, you might find your own applications for things. So the first one is sparse data. So the idea with sparse data, I mean, it was motivated by the fact that we solve lots of like very practical terrestrial problems. So like look around the room, and there's steel somewhere, right? But very, very few places. And so if you have a field in your simulation that's like the density of steel, to represent that everywhere on your mesh is like an absolute stupid waste. Right, it's 0, 98% of the time, and then you've got a few little spots where it's not 0. So what you can do, of course, is represent that sparsely. You can use various things like sparse matrix representations. There's a whole bunch that exist out there. The problem with these is that introduces indirection, and the minute you introduce indirection, you start to worry a bit about performance. So you lose things like vectorization often. There's lots of consequences to this. So our compromise is what we call dense on block. And the idea I'm trying to show it here. Imagine these blue blobs that are the thing that you're trying to represent. There's 2 of them here. And what you do is you allocate space and you operate on the data only in those blocks where somewhere on your block you have the thing. And so the green blocks here contain this whole region that has blue. So storage for the blue thing is allocated everywhere on the block. You operate everywhere on the block. Everywhere where it's not allocated, the data structures, the abstractions that we have allow you to transparently not worry about it. You just don't do any compute on the data that doesn't exist. And there's 0 cost in terms of indirection or any of that stuff. And so what we've done by implementing sparse data the way we have is basically we've kept all the advantages of block structured AMR, all the speed, all that simplicity, all this stuff, and we've also picked up the ability to massively compress data sets sometimes. So I'll give you an example of it in action. So this is a very simple sort of classic Hydra problem. It's a 3-material triple point problem that we've run in our code Riot that I'll talk about in a little bit. The bottom left here is the density. This is just the density of the gas. Top left, top right, and bottom right are the volume fractions of each of the 3 materials. So showing you where the materials are. Parthenon basically does all of this interesting stuff for us. The white regions in these movies are regions where those materials are just not allocated. And what you see is like, it sort of naturally adapts. The material's moving through the domain, the Parthenon notices that it's coming and it allocates the space for it. And what you get in the end actually is a whole bunch of compression, you get a much faster solution, and like bitwise agreement with what you had with the fully dense representation. And so we've sacrificed nothing. This is like not an approximation or anything like that. It's just being a bit smarter about how you store and operate on data. So that's like the sort of archetype of a usage for sparse data, but we found other uses that we think are pretty interesting. So here's one, same problem. Top left now is density. This is material density for 2 of the materials, and the bottom left is actually a measure of the change in the solution. So it's like some norm of the change in the state after a step. And what happens is that where there's nothing happening, that value is 0. The field gets deallocated because there's nothing going on. It's like it's 0. Why am I storing a bunch of zeros? And so it deallocates it. And now we've got a check in the code this was like 3 lines of code we had to add. There's a check in the code. If that field is not allocated, then nothing happens. You don't do physics at all. So there's no hydro update. There's no anything. And so a few lines of code, and suddenly now not only are we sparse data, but we're sparse physics. We're actually only doing physics where we need to, only where there's change, in fact, happening. And all this is just natural. Like we don't have to carefully code something that detects things. Like it's all behind the scenes. Parthenon just sees it and knows what to do. Okay, so that's sparse data. yeah, I think there's a bunch more applications. I had a conversation this morning about some chemistry stuff. We've been thinking about reaction networks in this context. So if you imagine a problem where you've got a domain where you've got a big part of it that's, say, in some equilibrium condition, and then you get a part that's reacting, you can use sparse data to not have all those species in a big part of the domain where things are just equilibrium. It's just algebra. You can figure out what the answer is, right? But then allocate it where you need the thing to actually do reactions. So there's lots of applications of the sparse data stuff that we are excited to see actually explored. So the next thing I want to talk about is task-based execution. So we've actually found this super useful. Honestly, I can't tell you in practice if this is super useful in the sense that it's made our code significantly faster, or like we're leveraging the tasking to do some like magical thing behind the scenes. It does buy you things like overlapping communication and computation, these sort of classical things that we could write without tasking, frankly. But what tasking actually, what I've found useful about it is it's really easy to write. So the way we write the tasking is the way that you think about writing a code like as a computational physicist. It's like, okay, so first I got to do this, and when that's done, I can go and do that. And then when that's done and this other thing is done, then I can do this next thing and so on. And that's literally how you write like the driver level piece of code for a Parthenon-based code, is you express the things that have to happen and what those things depended on happening, if that makes sense. It turns out to be quite simple. And behind the scenes, the task graph is built, and you can execute the task graph in parallel with threads. The task graph can actually be, this is a feature that I was excited when we got this working finally. It used to be a DAG, a directed acyclic graph, so it was one directional. You could express task dependencies and just like run through it and do all this stuff. Now you can have cycles in your graph, which is kind of fun. So you can express things like iterative solvers. You can express things like iterations inside of iterations. So you can do like a Newton-Krylov kind of a thing, for example. This is actually how we're using it now, is with sort of nested iterative patterns. And all the tasking stuff sort of figures all this out. It schedules everything, overlaps communication and computation wherever it can, all sort of naturally. Just a couple more comments on this. I already said this first one, is the expression of tasking. You don't have to build a graph or know anything about graphs. You just say, I want to do this, and then after that I can do this thing, and after that I can do this next thing. These tasks are different. If you've heard of like things like Charm++ or Legion, our tasks are very different than those tasks. Our tasks are local to a node. They don't know anything about MPI. In fact, some of the tasks that you add to this task graph are communication tasks. The tasking doesn't know anything about the fact that they're communication tasks. It just knows that they're a task. But it doesn't try to be clever. It doesn't try to reason about data dependencies, and then doesn't like ensure that your data arrived from some other node or something before it goes off and operates. It doesn't have to do any of that. And none of that is, this is maybe a hot take, but none of that is necessary. It's like, I think it's sort of attractive from like it's elegant, but that doesn't mean it's necessary or even really that useful. What you get for that kind of simplification is, I would argue, all the features of tasking that you want, but you get it in 400 lines in like one header, instead of 400,000 lines for Legion or 600,000 lines for Charm++. Like the level of complexity is just so dramatically reduced in this that I think that alone is sort of worth it. Okay, so there's more. I kind of wanted to leave breadcrumbs for kind of some of the thoughts on where we're going with some of the stuff. One thing that we can't yet do, but I think there's a pretty straightforward path to getting there through this tasking stuff, is integration of support of streams. So like on CUDA devices, for example, you can have streams that it can execute concurrently on the device. I think that there's a really natural way to pair streams with tasks so that you can sort of very naturally behind the scenes handle concurrent execution across tasks. That'll be fun. The other one that I'm anxious to see, and it's now sort of possible to do, before it made no sense, sort of an automated dynamic balancing of work between CPU and GPU. So now that we have architectures where you share a memory space and it's not super expensive to move data between CPU and GPU, you can start to think about actually leveraging both profitably, whereas before it's been kind of hard to imagine. So this is another space where like I think we can do this behind the scenes in Parthenon, and your code can leverage it without you having to really be an expert in all this stuff that like it's sort of too much to ask for many people. Yeah. Okay, so that's tasking. So domain decomposition and load balancing, I wanted to say a few things and also use this as an example of kind of this application-driven stuff. And Ed, maybe you'll appreciate something I'll get to in a second. So the sort of default way that we do this in the code is we have a block structure mesh. This is sort of like the standard thing everyone does for this sort of thing. You run a space filling curve through it. Space filling curves take this multi-dimensional space of blocks and basically collapse it and they map it into a one-dimensional array. You can chunk that array up into sort of equal size chunks and then you distribute that to ranks. That is great sometimes, sort of optimal in some sense, although that depends, optimality depends on exactly what kind of space filling curve you're using. The Morton order or Z order is not really optimal, but it's close enough. So you get things like this. And what's nice about this is, by the way, this is some AMR mesh. That line is the space filling curve. The colors are sort of the rank. It's meant to represent a rank that set of blocks has been assigned to. So what you see is that they're bunched up, right? They're spatially local to one another. There tends to be a locality that means that when all of these blocks, for example, sit on the same rank and you have to share data from this block to that block, that's not even touching the network, right? That just goes locally within your node. It's a memory transfer or whatever. So that has obvious advantages, sort of declogging the network traffic and so on. Obviously, it doesn't always work. These two, for example, have to go over the network. And then you get times when, like this, where the space filling curve jumps, and you got this like lonely, weird little block sitting by itself, surrounded by other ones, and then the rest of them on that node are sitting up there. So that's just, you live with this sort of stuff, right? It's not perfect, but it's pretty good. In the context where the work per block is equal. So if you have a very simple workload, it's a pretty common workload. So I say very simple, but really it's quite common. If your workload per block is equal, so that like you're doing exactly the same thing on every block's the same size after all. So if you're doing the same things, it should be the same cost. This is basically perfect. You get a balanced load. It's super fast. This is easy to compute. You can show scaling, as I'll show you in a bit, out to basically infinity. Like it scales and scales, and there's no issues. The problem comes in when what I just described is not true, when you don't have equal work per block. And there's actually quite a lot of reasons why that might be the case. And in fact, I even bragged about one of the reasons that can drive this kind of sort of variance in cost per block, which is the sparse data stuff. So there's lots of reasons. Sparse data is one. Local iterative solvers is another one. If you're doing some kind of iteration, sort of non-deterministic in some sense, how long it takes to converge. That'll change from cell to cell, block to block, and so on and so forth. You can actually use some of the mechanisms in Parthenon to do different physics on different blocks. And obviously that can come with different costs then per block. And if that's the case, then what do you do? Because the default strategy that I just described is going to just chunk up equal numbers of blocks and send them out to ranks. And if you do that and they cost a different amount, then you're wildly imbalanced. And that's obviously problematic. One way to handle that, which is something that certain code bases do, is to look at the work and pick up a task in the middle of a cycle. It's like, okay, I see that there's some resource over here that's available. I have too much work to do over here. I'm going to pick this task up and the data that's tied to it. I'm going to ship it across the machine. And I'm going to leverage that resource over there that's currently unoccupied. I don't want to get into like a religious war here, but that's the wrong way to do this kind of load balancing. For the kinds of like tightly knit HPC workloads that we're talking about here, the data movement just completely kills you. You can't afford to do it. And so you have to be more careful, more methodical about when you're allowing the system to actually move data around. And so the way that we are tackling that, and we've had really great success, and even in the face of all the sparse data stuff and different physics and iterative solvers and all this stuff, is by essentially just instrumenting the code to time tasks. So we can do this in sort of an automated way. You get a time for a task. It's a cost. And then instead of chunking up your space filling curve into equal chunks by counting the blocks, you chunk it up by sort of equal sums of costs. Seems pretty straightforward, right? So that works fantastically on CPU. In principle, it should work on GPU, but getting a portable implementation of this turns out to not be as trivial. So we're working on it. I think we're going to get there pretty soon. So this is sort of work in progress that I think we'll have done in the short term. Okay, but sometimes that's not enough. So what if, in fact, the space filling curve is not great? So here's an example, again, application-driven stuff. So one of the things that we do at Los Alamos, it turns out, is radiation transport. A popular way of solving the transport equation is by a method called sweeps. There are folks in the room who certainly know all about this, much more than I do. In fact, essentially, and forgive me if I'm being a little fast and loose with the language here, but basically you've got an advection equation. In this case, I is meant to be specific intensity. I'm thinking about thermal transport. And when you discretize this with a backward Euler method and you just do upwind advection, it turns out that you can exactly invert that discrete system. It produces a linear system. You can exactly invert it with this method called sweeps. And it basically starts in the corners of your domain where you know the boundary conditions, and then it just marches downwind. And the discretization is upwind, and so you always know everything you need to know to push the solution. I'm looking at these guys who all are judging me. And you can march the solution across the domain, and you get an answer in one pass over the data. So it's sort of amazing, right? You get an order n solution to this implicit discretization. So here's what it looks like. The red boxes are active blocks in the mesh, and the whole thing, this is one time step. The whole thing proceeds in stages. So this is like a movie showing you the progression of updates. All these little things are blocks, not cells. These are all blocks, so they're like 16 squared or 32 squared, lots of cells, right? I'll play it again. So what you see when you watch this movie, I saw sort of stars. I find it mesmerizing, actually. But what you see are times in this movie where if you look at the distribution of active blocks, it looks completely crazy. Like there's no real structure to it. It's just like, it looks like scattershot, right? So I'll tell you one more time, and I'll point out the scattershot. So some of this looks fairly structured, but you look at it like this, like what's happening? It's totally, how do you write a code that can deal with that kind of sort of weird structure, right? And that's particular to this particular mesh that we're doing the sweep on. So in general, as the mesh adapts, like this is going to be a problem, right? That's the point. The space filling curve decomposition of this problem turns out is like wildly terrible. It makes a lot of sense for things like hydro, stuff that you might do with like explicit, discretizations, the classic sort of PDE stuff that you would do for that kind of stuff. But for sweeps, it's absolutely awful. So if this is the space filling curve decomposition of that mesh, looks nice in principle. If you look at how many active blocks each rank has in that decomposition as a function of stage, what you find is that like you get just totally crazy imbalance. You get some that have like no blocks active at all for big stretches, while simultaneously some other rank has like, infinity blocks to update. It's wildly imbalanced. And so the challenge here is to somehow find a way to do a decomposition that balances the work per rank across this entire span of stages, which wasn't obvious existed. But it turns out that it does, or at least we think it does, and it seems to work whenever we apply it. This is a very heuristic thing. I'm not going to get into the details. But if you look at this blue curve, that's the maximum number of active blocks per stage across all the ranks in that decomposition. And then if you ask, like, what is the optimum? What's the best thing I could do? It's just the number of active blocks per stage divided by the number of ranks. That's this black curve on the bottom. These other curves are different decompositions, a different strategy for decomposition that is not a space-filling curve. I've shown two extreme examples, the orange one here and the red one. So this is the orange one and this is the red one. So we have a method that basically produces a discretization, or a decomposition rather, that tries to do what we asked, to give equal work across all the stages of a sweep on an AMR mesh. And we have a parameter. And the parameter actually turns out to be super useful. The parameter controls the degree of locality in your decomposition. So you get really, really good, on paper at least, 3% overhead. That is to say, if you integrate up onto that orange curve, it's 3% larger than the black curve. So it's almost perfect. And that produces this, which like has no locality at all, basically. Every block is next to some block on a different rank across your entire map. It almost looks like you just like randomly assigned blocks to ranks. It's not, but that's what it looks like, right? You can dial a parameter, though. You get a little less efficient, up to 13% loss in efficiency. And you get this, which now you can start to see structure, right? There's lots of locality. And we can quantify what that means and so on. And so we've done this sort of thing. So this is like a little bit of a sidebar. What this is motivating in Parthenon is one of these customization points. So this is what I was getting at earlier. We can't come up with a decomposition that's going to be everything to everyone. What we can do is identify those points in the code where sometimes you need to do something special. You need to have your own special sauce for your own needs. This is one of those points that now we've discovered. And so this is a thing that we're gonna put into the code, a customization point to introduce your own decomposition. Yep. Okay. Forest of octrees. Really, all I wanted to say here is that we're not a single octree code, which is like you're constrained to have like a box and do things. What we have is actually essentially just like a list of boxes, and each of those boxes can independently refine. And that allows you to actually do some fun things. So like you can build a mesh like this with like a weird angle, and that's actually fine. You couldn't do that if you didn't have a forest of octrees. You can also do things like have odd points of connectivity. Like this is a 3-valent node. We can support things like that. You can support a 5-valent node. So you can have meshes that are non-trivial. The reason we started doing this, again, everything's application driven. The reason we did this one is because we're also on the side at a very low level writing a nail code, so arbitrary Lagrangian or Larian code, so a moving mesh code where we have to have things like this as part of that. Okay, most of the rest of this is going to go pretty fast. I know time is running short. So I want to just flash the scaling results up. Yeah, I'm getting there. That's yeah. I'll try. You gotta give me another half an hour then. It's a negotiation, right? So I wanted to show mostly just this number. So Parthenon, or a code written on it, Athena PK or Parthenon Hydra, I actually don't know which one, but it doesn't matter. They're basically the same. Has been used in acceptance testing on Frontier because, frankly, it just works really, really well on the machine. So they were able to show 92% weak scaling efficiency out to 74,000 GPUs, which is like about as good as you can do. So that works great. Strong scaling works great. This particular thing, if you know, Hydra solvers, 20 trillion cell updates per second is just a lot of updates. Like you can do a really big problem at this scale. So that was that. There's stuff I'm not going to talk about. This is mostly like, oh my God, that's terrifying looking. That's why I flashed this up. The code's instrumented, so you can understand, even in the context of a code that's like doing things dynamically, all this tasking stuff. It's very difficult to reason about sometimes. It's got the stuff that can produce plots, I guess, to help you understand how the code's actually executing. So you can dig in and understand things, see what's going wrong if something's not working the way you want. Okay, so from here, mostly it's just codes written on top of Parthenon. So I'll flash through some of this. There is a point to each one. This is actually a poster that was produced as part of a summer school at Lanel. So this is like a 10-week project with grad students. And they took Parthenon and built a code to do type 1a supernovae in a summer and produced stuff that worked. Didn't solve the type 1a supernova problem, but it worked. This code Karma is general relativistic MHD. They use it for modeling accretion disks around black holes, particularly for the Event Horizon Telescope, which you may remember from some New York Times sort of front page picture of a black hole, right? This is that science. So one of the main codes that collaboration uses now, it's called Karma. It was written by a student during a semester at Lanel named Ben Prather. He's now a postdoc at Lanel, but he wrote this code in a semester. And it is like an insight, yada, yada, yada. It's a big code that lots of users. Athena PK is basically the Parthenon port of Athena++. It doesn't have all the physics, but it has a set of physics, and they're going after things that I know the astronomy department here actually also looks at, and so there might be some interesting opportunities with Athena PK. A lot of these codes are open source, by the way, including this one. This is something totally different. There's a group at the lab who's looking at tokamaks. This is a simulation that does a multi-rate integration of a coupled kinetic and sort of quasi-steady MHD scheme. They're looking at what are these vertical disruption events. There's like anomalies that that lead to basically failure of confinement of the fusion device or the plasma in tokamaks. And so this is like just a very different looking thing, right? They're doing particle and cell, and so like nobody's written a particle and cell code on top of this, but you can do it because the basic facilities are there. Flash is a pretty widely known code, lots of users and so on in HEDP and Astro and so on. I mean, there's some numbers up here, 3,900 users, 1,300 papers and so on. Flash is porting on top of Parthenon now. So this is like a status report. This was back from November. I assume they've gotten further now. But that's their plan of record to get onto GPUs and things. Artemis is a code, Artemis and JBen. Together, this is a rad hydro capability for looking at planet formation. It's a super interesting problem. It's very timely with things like JWST out there and so on. This is a code that they put together in 1 year as part of this project that does all the things essentially that they need. It's got like, sort of a multi-fluid thing. They've got like dust models and coagulation and radiation through Monte Carlo, and they get great performance and all open source just recently. In fact, one of the developers of this code is again, Patrick. Keep going back to Patrick. And so I think there's lots of interest in planet formation here at Michigan, so that'd be a great opportunity. Phoebus is a relativistic astro code that we wrote on top of Parthenon. It does various things, including dynamical spacetimes. The target, which we're not there yet, so these are pictures from other codes, but we're close, is core collapse supernovae, which is like a big, horrible 3D radiation hydro problem. Neutrinos in this case, not photons, not neutrons, it's neutrinos. Sort of interesting, and basically the same physics for this, which is compact object mergers, merging neutron stars, things like that. So again, looking for collaborations here. I mean, we've got a student now, Yihan, who's gonna look at core collapse, right? This is like kind of most of my time these days is spent thinking about this code called Riot, which is the code we've been developing now for a few years on top of Parthenon. It's got a growing list of physics. The priorities have been shifting and so on. These days, we're pretty focused on producing a code for high energy density physics, modeling high energy density physics experiments. So things like lasers, stuff like this. It's got a bunch of different physics. Also a variety of methods. So like the sort of standard thing is second order hydro and so on. We've also got fourth order methods in the code. So it supports both inline, all the facilities are sort of supported. I know we're getting close here. This is an example, an early example of sort of an HEDP-like experiment. Just wanted to show a pretty movie of something that was run in Riot. So this is like a shock. It's an ablation-driven shock off some ablation layer that goes through and produces all this fun instability growth, which can be diagnosed in experiments. So we're working on that stuff with collaborators here already, actually, people like Carolyn Carranz. Almost there. Riot is fast. We wrote a report up that, again, to go back to the very early motivation, right? Comparing a block structured code that did the kinds of physics we care about at LANL with X-Ridge, which does cell-based AMR, but a similar set of physics. You can go off and compare, do some analysis to try to understand what's going on. What we found was that not only can this kind of a methodology be used on lab kinds of problems, it's actually extremely effective at solving lab kinds of problems. Depending on your metrics, it's either way faster or like absurdly faster. Those are the only two. The memory footprint, in spite of having like 5 times as many cells, is lower because of the sparse data that we're using. So there's a bunch of advantages to doing this, and there's a whole bunch of different kinds of problems this opens up. I wanted to say, I have one more slide, the conclusion slide, but I want to say like this is a significant focus for the sort of partnership that we're building, at least in the early phases here, around like myself and Patrick, who's coming, or who's here already. Another collaborator, Jonah Miller, is moving out in about a month. Chad Meyer is moving out in maybe May, June. All of us work on this code base, and this is an opportunity, I think, to do a lot of different kinds of modeling. We could work on methods, we could work on physics, we could work on computer science, we could work on lots of things with this as a vehicle, and so I'm super anxious if people are interested in learning more, talking about opportunities and so on. And it's not open source yet, but it will be very soon.
No, Parthenon is open source.
Parthenon is, Riot.
This particular part.
Yeah, this particular code, Riot, on top of Parthenon. That bit is not yet open source, but it will be soon. Okay, conclusions. I'll just really quickly. I think that there's value in having a tool where you can you can still write basically all your methods and algorithms. You can understand what your code is doing at a pretty deep level, but not worry so much about all the horrible things that you have to worry about, including just the pace at which machines are changing and all this sort of stuff. I think that Parthenon can do that for a pretty wide range, not everybody, but a pretty wide range of applications, and I think that's value added. I think that the application focus that we've had in developing Parthenon has led to a code that is not super bloated. I think all told, Parthenon is maybe 40,000, 50,000 lines of code. Lots of other similar capabilities you can look at are like an order of magnitude bigger. And so I think that's an advantage for us, makes us more agile, which again was part of the goal. Customization points I mentioned, I think are crucial for certain things. There's like 10 downstream codes. I showed a fair number of them, many of which are open source. And we're super excited about potential collaborations. So I'll end there. I answered everything. Oh.
So if I may be mistaken, but I think all of the applications that you showed were time dependent. Is that correct?
Oh, yeah. Yes, I think that's true.
And you use operator splitting?
Yeah, so Parthenon provides some sort of integration stuff. So there's like some RK integration things and things like that in there. Mostly the choice of integration strategy and coupling strategy between packages and so on is up to the downstream developer. That's sort of what you express in like the driver in Parthenon lingo. And that's important for you to be able to express. So there are things that Parthenon provides that are convenient. If it turns out that you can use RK2 or RK4 or whatever, like those are there. But if you need something else, you can write your own. And so it's really flexible. Often for us, right now, we are largely for like, when we do, let's say, rad hydro, and you're doing like radiation diffusion or SN or something like this, that's typically the way we do that. It's just operator splitting. So we do hydro and then operator split radiation update and move on with their life. That's good enough sometimes and probably not good enough other times. And so that would be a great example of a collaboration that would be exciting to have, to talk about that more.
I had a question about the sparse solution-based approach that you showed. How do you guys manage the boundaries? Because the mesh feedback, the blocks essentially are dynamically allocated. How do the core cells operate? Because usually, for example, in other block structured cores, right, you have an underlying mesh that can be a bit coarser, and the solution is interpolated in space or time, essentially. So how do you guys manage that, essentially? That's what I'm curious.
So I'm not entirely sure that I'll try to answer your question. Tell me if I got it right. So there's only one mesh. Lots of codes that do AMR will have like all the levels represented. We don't have other levels. We just have the top level or bottom level or whatever level you'd like to call that cell. So that's one piece. When it comes to doing like, as the movie was trying to show, like as things move across the domain, obviously you need to like allocate storage before you can like send and receive a piece of data. So all that is done behind the scenes by basically sending around a flag, essentially, like you've got data incoming. All that kind of stuff is handled by looking at the values of sparse fields and comparing with a user settable threshold in the cells that are like that would be sent to fill the ghost cells of your neighboring block. And so the minute anything enters those cells, the code detects it, sends a flag, it says allocate your stuff and expect to get data, and it gets the data. And so that's why there's like literally zero difference, like bitwise agreement when you run with and without sparse, is because like anytime anything is there that it could possibly share between blocks, it sends the message. Allocate, get ready, and go. Does that answer your question?
Yeah.
Good.
I have a kind of exotic question.
Perfect.
You said they were future-proof early on.
I did pause to be.
Trying to get you to think about what kind of architecture changes could you foresee that might break your framework?
Yeah. So that's actually why when I said it, I cringed a little bit, because who knows what the future will bring. If things go the way, actually Ritu should. Here, you want to answer this question? If things go the way they seem to be going, again, memory is like the big challenge. I think memory's been the big challenge for a while. My read of the tea leaves, and from talking to people who know much more about this than I do, it seems like things like, like reading like dense arrays and things is just going to get faster and faster and faster, and dealing with sparsity is going to not. Unless magic things happen, which maybe will happen as part of this collaboration, in fact. Maybe. But I think that suggests, to me at least, that like, at least for a while, this notion of block-structured AMR, while it does produce more cells, in principle more work than like a cell-based method might, or like, that you might use a particle method or something like this that might allow more sparsity or something in the problem. All those methods suffer from indirection and like the lack of a dense representation in memory space of your data. And so I think I'm pretty comfortable for a bit. Future-proof is a strong word though, so who knows?
I have a follow-up on that. So maybe two questions in one. All the AI accelerators that are out there,
Yep.
right? So what do you need to do to exploit them better behind the hood? Maybe I'll answer the first part, then I'll get to the second.
Yeah, so that's a great question. And when you say AI accelerators, like my head goes to like tensor cores and things like this. I don't know if that's
the ground level.
yeah, well, that's the kind of guy I am. So, like I think like GPUs, if you think about GPUs as AI accelerators, then like certainly we're already on GPUs. We can leverage those really well. If you want to talk about the little bits on a GPU that can do cool things like tensor cores, then you got to have bigger conversations around things like mixed precision, and like it opens up a whole other kind of orthogonal axis to the ones that we're talking about here. I think that's super interesting stuff to explore, and I'm actually pretty confident that there are good use cases, and I think use cases that we can expose in Parthenon, but we haven't yet had an application that has driven us there. So
I think the Blackwells may already have some options. The second thing is, from a computer science, maybe this is Ritu's question, or a future Ritu question. By better utilizing computer science principles, how much more do you think we can go, right? With what we have right now,
Yep.
and then the next level, right? So kind of, roughly the kind of things Ritu is working on. So
Yeah, like I guess
Yeah.
maybe performance portability, and then you were also saying utilizing both CPU, GPU together.
Yeah.
Like, there's a lot of breadcrumbs you laid out in your slides, right?
Yep.
Where do you think? Is it 2x, 10x?
yeah, we want to know an X there. Yeah.
You want an X?
Yeah.
Oof.
And again, it depends on the application.
It depends on the application.
Disclaimer, but
So
beyond that.
yeah, I mean, so my gut tells me that, for example, doing the stuff behind the scenes that allows you to do CPU and GPU simultaneously is like a 2x. That's not. I think we could get to 2x. I mean, the details depends on lots of things, but like 2x is. I think you could probably get to roughly that.
Matt at Ihan's PhD, 10 years to 5 years.
Hey, I'm sure he's excited to hear that.
But then, in terms of future hardware design, again,
Yeah. So
not far ahead in the future. Right?
Yep.
5 years.
Yeah. So like I am. There's different perspectives on this. I think that like some of the work you guys are doing has the potential to change some of the arguments that I gave, or at least it changes the crossover point between like when a method like this that is fully dense and so on, when that wins versus something that exposes more sparsity and so indirection, but can leverage some of the stuff that for example, you guys are working on. I think that the point of transition will change. I think it's just going to be the case though that like for at least as far as I can see that dense is just going to be faster. And I don't think what that will be great for is if you've got 1 million lines of code that are indirect and sparse, and that will speed that up by a non-trivial X. You want an X, I don't know the number, 5X maybe. I'm just making up numbers now. Like I could make up numbers all day. That stuff I don't think is going to help us because we're just totally dense. What's going to help us is like the the sort of methodical progression of technologies that are just moving forward and forward faster and faster. HBM, for example. That's going to be the thing that drives us. And that was intentional. It's why we did this. Because like, we can kind of count on that the same way we historically counted on things like Moore's Law and stuff. Is, you know, it's a similar kind of thing. So.
Nothing at all? All right, if not, thank you very much for